Welcome students to the video module on the topic Hamiltonian formulation. In the Lagrangian formalism, Lagrangian is defined as a function of generalized coordinate qj, generalized velocity qj dot, and time. Okay, Lagrangian is defined as a function of L of qj dot, and t. The Hamiltonian put forward an alternative formalism called Hamiltonian formulation, in which the physical quantity can be described by a function known as Hamiltonian function, which is defined as a function of generalized coordinate, generalized momentum, and time. Okay, so in Hamiltonian formulation, we define a quantity, a function known as Hamiltonian function, which is a function of generalized coordinate qj, generalized momentum pj, and time t. So in case of Lagrangian, we define that function as a Lagrangian as a function of qj dot, and t, while Hamiltonian is defined as a function of qj, pj, and t, where pj is the generalized momentum. So from Hamiltonian function, we can derive the governing equations of any dynamical systems. The Hamiltonian equations are first order differential equations, whereas in case of Lagrangian formalism, there we defined second order differential equation known as the Lagrange's equation. It was a second order equation, but the equations that we use in Hamiltonian is a first order differential equation. Okay, now we know that in case of Lagrangian, we defined configuration space. Okay, so to describe a physical system, we require a reference coordinate with respect to which all measurements can be made. So in Lagrangian, we used configuration space. The same way, what will be the reference coordinates in case of Hamiltonian? Hamiltonian is a function of generalized coordinate qj, generalized momentum pj, and time t. So if the system consists of n particles, then we need 3n generalized coordinates, then 3n generalized momenta. So totally there will be 6n coordinates will be there. This 6-dimensional space that we use for defining this Hamiltonian formalism is known as the phase space. Okay, so by substituting equation number 2, the equation number 1 can be written as dl by dt equal to sigma I. Instead of this del by dou qj, we can write d by dt of del by dou qj dot. That is why d by dt of del by dou qj dot times qj dot. So qj dot. It is not qj double dot, it is qj dot here. Plus then del by dou qj dot, qj double dot, plus del by dou t. So this gives, or this can be simplified by using the product rule, sigma j d by dt of del by dou qj dot del by dou t. This is a UV function, a product rule. We can apply the product rule for differential. D by dt of UV is u times dv plus v times du. The same rule here. That is why this expression simplifies to this one. Actually, d by dt of del by dou qj dot times qj dot is d by dt of del by dou qj dot plus del by dou qj double dot. So the differential of first function into second function plus first function into differential of second function. That is, using that rule, we simplified into this term. But we know that the momentum Pj is equal to dou L by dou Qj dot. So we can write again dl by dt is equal to sigma j d by dt of, instead of this dou L by dou Qj dot, we can write Pj, then there is a Qj dot plus dou L by dou t. Now rearranging this, sigma j d by dt of Pj Qj dot minus dl by dt is equal to negative dou L by dou t. Now taking the differentiation common, to apply commonly, we are applying to both, that is d by dt of Pj Qj dot minus L equal to minus dou L by dou t. So the bracketed term is known as, or we call that term as Hamiltonian of the system. So Hamiltonian H is equal to Pj Qj dot minus L. Now we know that, we are further simplifying. So we know that for a conservative system, the potential energy V does not depends upon the generalized velocity. So dou V by dou Qj dot, Qj dot is velocity, Qj is coordinate, Qj dot is velocity. So dou V by dou Qj dot, this V is potential energy. So dou V by dou Qj dot is equal to 0. So we know that, we already know that the Hamiltonian is defined as H is equal to sigma Qj dot Pj minus L. But what is L? L is actually T minus V. So we know H is equal to this term here, and we just introduce a term V there. So L is T minus V. Then we differentiate this sigma j Qj dot dou by dou Qj dot of T minus, there was actually a term dou by dou Qj dot of V. V is the potential energy. But since potential energy is not depending on the Qj dot factor, Qj dot is actually velocity. So potential energy does not depend on velocity. That is why, expanding the bracket, there was a term dou by dou Qj dot of V, but that is 0 because potential energy does not depend on Qj dot. Qj dot is velocity minus L. There is an L that is still there. Now H is equal to sigma j Qj dot dou by dou Qj dot of T is being substituted half mv square, that equation. So half mj Qj dot square minus L. So H is equal to sigma j Qj mj, we differentiated the half mv square, mqj dot square is differentiated, so 2 mqj will be there, mqj dot will be there, so 2 cancel. So what is remaining is qj dot mj Qj dot minus L. So there are 2 qj dots, so Qj dot square sigma j mj Qj dot square minus L. What is this mv square? It is twice the kinetic energy, because kinetic energy is half mj Qj dot square. So mj Qj dot square is 2t. So 2t minus L. Now substitute for L. L is t minus v. The Lagrange function L is t minus v. Simplify 2t minus t plus v. So one of the t cancel. So t plus v. The Hamiltonian of a system is defined as H is equal to t plus v. That is the total energy of the system. T stands for kinetic energy and v stands for potential energy. Sum of the kinetic energy and potential energy, or the total energy of the system, is described by the term Hamiltonian. Now we have to find Hamilton's canonical equations of motion. Just like we learned Newton's equations, and here also we are finding Hamilton's canonical equations of motion. So how can we find the equations of motion using Hamiltonian concept? So we defined Hamiltonian function H is equal to H Qj Pjt. That is, Hamiltonian is a function of coordinate, momentum, and time. Now again we differentiate, we are differentiating actually dH by dt. What is that? dH by dt or dH is equal to, we have to do partial differentiation because H is a function of Qj, Pj and T. So dH is equal to dou H by dou Qj dQj plus dou H by dou Pj dPj plus dou H by dou T dt. So these are the partial differentiation. First with respect to Qj we did, then with respect to Pj that did, then with respect to time. So we got this expression. So let that equation be there. Now we also know that Hamiltonian of a function H is given by Qj dot Pj minus L. You differentiate, dH will be, dH is equal to, what will be dH? This is a product. So you have to apply product rule. Qj dot dpj plus pj qj double dot. Okay, pj qj dqj dot minus dl. But you know, Lagrangian L can be written as a function of coordinate, velocity, and time. So L is L of qj dot t. Here also we are applying the partial differentiation. So dl is equal to dou L by dou qj dqj plus dou L by dou qj dot dqj dot dou L by dou t dt. But we know that dou L by dou qj dot is momentum pj. Dou L by dou qj dot is momentum, and dou L by dou q is p dot. Dou L by dou qj dot is p, and dou L by dou q is equal to p dot. Substitute these two terms in the above equation. We'll get dl is equal to pj. See, instead of this dou L by dou qj, we substitute a pj. Pj dqj plus, now instead of this dou L by dou qj dot, we substitute pj. So pj dqj dot plus the last term remains dou L by dou t dt. Now again back to the equation for Hamiltonian differentiation of Hamiltonian. dh is equal to sigma qj dpj plus pj dqj minus d. It was dl there, but this dl is now going to replace with pj dot dqj plus pj dqj dot plus dou L by dou t dt. Now sometimes gets cancelled, like terms like pj dqj dot. Here this is a small error. It is pj dqj dot that gets cancelled. So dh is equal to qj dot dpj minus pj dot dqj minus dou L by dou t. This term and this term cancelled. Okay. So we have two expressions for dh. You can see that we derived dh is equal to dou h by dou qj dqj, dou h by dou pj dpj, dou h by dou t dt. And also dh is equal to sigma qj dot dpj minus pj dot dqj minus dou L by dou t dt. Now we can compare the coefficients of similar terms here. dqj is here and here also dqj. So that means pj minus pj is equal to dou h by dou qj. So pj dot is equal to minus pj dot. It was minus pj dot, that's equal to dou h by dou qj. So pj dot is equal to minus dou h by dou qj. The same way, the coefficient of dp, here it is dp, that is dp here. So we can write qj dot is equal to dou h by dou pj. Qj dot is equal to dou h by dou pj. And the last time can be compared to get dou h by dou t is equal to minus dou L by dou t. So hence we got the Hamilton's canonical equations of motion. And you know, these equations can be applied to many mechanical systems to simplify or to derive their expressions. Such methods we applied in the case of Lagrange equation also. So here also we can use. The advantage of Hamilton equation is that it is a first order differential equation, and where the Lagrange equation was a second order differential equation. But the thing is that for setting up a Hamiltonian, we have to first set up the Lagrangian. Then only we can move to the Hamiltonian formalism. So that is one disadvantage. Okay, anyway, let us learn a few applications of Hamilton's equations of motion. Okay, the first one is linear harmonic oscillator. What is a linear harmonic oscillator? It is a type of linear harmonic oscillation is a type of oscillation in which acceleration is proportional to displacement. The string, if it is released, it will execute a type of to and from motion, which is known as a linear, linear harmonic oscillator. Okay. So in order to apply linear Lagrange, Hamilton's equation to this, first of all, we have to set the Hamiltonian. But for setting Hamiltonian, we need the Lagrangian also, because now H is equal to T plus V. And Lagrange's equation L is equal to T minus V. T is the kinetic energy, half mv square. But here V velocity is replaced by x dot square. Minus the potential energy of a oscillator or a spring is half kx square. So we substituted that. Also, using this, what is actually P? momentum P is dou L by dou x dot. So dou L by dou x dot. When you differentiate this with respect to x dot, you will get half times m times 2x dot. So 2 cancels. So that will be mx dot. So P is equal to mx dot. So what is x dot from here? X dot is equal to P divided by 2m. Okay, now again back to the expression for kinetic energy. We know that kinetic energy T is equal to half mx dot square. Instead of x dot, you substitute P by m. So that will be half times m times P square by m. That is equal to P square by 2m. Now Hamiltonian H is equal to T plus V. The T is replaced by P square by 2m and V is half kx square. Now we know that the Hamilton's equations of motion. What is that? P dot equal to minus dou h by dou qj. Here, the generalized coordinate is displacement from the main position, that is x. So we can replace the generalized coordinate to x. So P dot here there is only one generalized coordinate. So P dot is equal to minus dou h by dou x. That is equal to, the differentiation is with respect to x. So the first term is not including any x, so we have to differentiate only the second term. So that gives to an answer half times k times 2x. So 2 cancels and that will be kx. But there is a minus sign, so minus kx. And the second Hamilton's equation, x dot equal to dou h by dou p. X dot equal to dou h by dou p. So dou h by, you have to differentiate with respect to p. That will give 2p divided by 2m. So 2 and 2 cancel. So that will be p divided by m. X dot is p by m. Now you have to find x double dot. X double dot will be, you have to differentiate this term again. So that will be p dot divided by m. But we know that p dot is equal to negative kx. Yes. P dot is equal to negative kx. That is from the first Hamilton's equation we derived. Substitute that here. X double dot is equal to minus kx divided by m. That is minus k by m times x. Cross multiply. It will be mx double dot is equal to minus kx. What is mx x double dot? Is acceleration. So m times a is equal to minus kx. That is F is equal to minus kx. So we define the expression for force. F is equal to force on a stretched string. It is also known as Hooke's law. F is equal to minus kx. So there may be questions like derive Hooke's law or derive the expression for force in terms of spring constant. Such questions can be asked. Okay, so omega is actually theta dot d theta by dt. So substitute the r omega is replaced by um, L theta dot, because here the r is L and omega is theta dot. So L theta dot. So now the kinetic energy is half mv square. So instead of v, substitute L theta dot. So that will be half m L square theta dot square. So we got that expression for kinetic energy. Now potential energy V is equal to, we already learned V is equal to mgh. But here, what is the depth from the equilibrium position? That is L minus x. That is why mg times L minus x. But L minus x divided by L is cos theta. So L minus x equal to L cos theta. So they substituted. So here, potential energy is equal to negative mg L cos theta. Now Lagrange of a function L is equal to T minus V. So T is half ml square theta dot square plus, I'm sorry, minus mgl cos theta. So there will be plus mgl cos theta. But the momentum P is equal to dou L by dou qj dot. Dou L by dou qj dot. So only the first term you have to differentiate. So m L square times 2q. So 2 cancel. So that will be ml square theta. Then Lagrange Hamiltonian of a system H is equal to T plus V. So we substitute for T the kinetic energy and V the potential energy. So H is equal to this expression. Now we can use theta dot is equal to P0 divided by ml square. Okay. But theta dot is equal to P0 divided by ml square. So H is equal to, we can substitute for this ml square theta dot square, ml square theta dot. So on substituting, theta dot can be replaced with P0 by ml square. So P0 square divided by ml square. One more L square was there, but that is cancelled with the L square already existed there. So mgl cos theta. Now using Hamilton's equation, so there there are two generalized coordinate here. I mean, one is theta and other is momentum. Theta is the generalized coordinate and p is the momentum, generalized momentum. So p0 dot is equal to minus dou h by dou theta. So we substitute for this. It is a differentiation with respect to theta. So the answer will be minus mgl sine theta. First term, no need to differentiate the first because it is not a function of theta. Now, theta dot is equal to dou h by dou p. Then we have to differentiate first term. That is because it consists momentum p. So dou h by dou p is equal to p0 or p divided by 2 ml square times 2. So 2 cancels and p0 by ml square. Then again differentiating this, theta double dot is equal to p0 dot divided by ml square. So theta double dot is equal to, what is p0? It is minus mgl sine theta. So p0 dot is minus mgl sine theta by ml square. One of the m cancels, one of the l also cancels. What remains is theta double dot is equal to minus g by l sine theta. This is the equation that we learned for the case of simple harmonic motion. I mean a simple pendulum. That is theta double dot is equal to minus g by l sine theta.